Hello, everyone. We got about 2 minutes before class starts. Feel free to ask me any questions. I have decided, instead of jumping to chapter 14 like my original plan was, I decided to go ahead and spend today doing some more relativity. So just to make sure, even though I've given you a plethora of examples on the actual links to my YouTube channel, and so in Canvas, you'll see a bunch of links there. That's certainly a lot of examples, but I wanted to give you a couple more because it seems I have a little more time than I expected. And the fact that chapters 14 and 15 take very little time. I would, if I was you, start working on 14 and 15, reading it and so on. I have set the due dates for all the homeworks, including chapters 11, 36, 14, and 15. They're all set now, so hopefully you can do them appropriately or whatever. So anybody have any questions before we get started? All right. Another student coming in. Got about 10 of you guys, 11 of you guys in here. Again, guys does not a gender thing for me. So I just use the phrase guys for everybody. So okay. All right, it's 5:20 now, so I'm going to go ahead and get started. So last time I gave you some very specific information about the two principles of relativity. I want to remind you that they are one, the laws of physics are the same for all inertial observers. So again, inertial observers, any reference frame that you look at that does not appear to suggest Newton's first law of motion or Galileo's law of inertia is being violated. If you find a reference frame in which that is not happening, that principle is not being violated, then it's an inertial reference frame. And again, as I told you, Einstein's idea was that he was working on the idea that perhaps gravity is not really a force as much as it's a fictitious force, not unlike the centrifugal force that you think you feel when you're riding the passenger side of a car and someone takes a strong left turn and you feel like you get thrown out to the right-hand side of the vehicle. That's actually your body trying to continue going straight the direction you were going at the velocity you were going, but because they turned this way, that compelled you to try to keep going straight, and the door pushed you in and provided the centripetal force required to keep you in that circle. If you happen to have been sitting on a bench seat with very low friction, for instance, you would have slid right up against the door. So that's it's something that feels real, but it's not a centrifugal force. There's no such thing as a centrifugal force. And not only that, centrifugal would suggest that it's pointing out. In reality, if you look at the circular path that something's following, then at any point, the path is tangential to the curve. So if you're going around a curve that, say, I was looking for something round, but all I see is, oh, here's something round. Okay. So if you're going right here, your velocity is that way. If all of a sudden the car turned to the left, then you would continue going this way. You're not going out that way at all. Okay. So in that sense, centrifugal force is a fictitious force. I also showed you in chapter 11, we talked about the Coriolis force, even though I told you weren't going to be responsible for that. But that's another force that really is just a ramification of using an accelerating reference frame. So similarly, Einstein said, hey, we can't see the force of gravity reaching across space, grabbing things and pulling it towards them. So maybe that too is a fictitious force. And I'll leave it out by talking about inertial reference frames. And that's the difference between special relativity and general relativity. That first principle, the laws of physics are the same for all inertial observers, is a special relativity principle, whereas in general relativity, that becomes the laws of physics are the same for all observers. Okay. The second principle of relativity is that the speed of light is a constant, independent of the motion of the source and independent of the motion of the observer. And then from that, as you can see in my YouTube channel videos, you can derive length contraction, you can derive time dilation, you can derive the Doppler effect, you can derive the energy and the momentum being gamma mv, the kinetic energy being gamma minus 1 in parentheses times mc squared, the total energy squared equaling p squared c squared plus parentheses mc squared squared. All of that can be derived using Gedanken like Einstein did, and get some explanation and some ramifications of the laws of physics. One of the things I mentioned we lost was, in fact, the idea of simultaneity being a universal thing. So, for instance, if I say two events happen at exactly the same time, I would say they're simultaneous. But you, if you happen to be riding by me with some velocity, you are thinking that I'm riding by you with the opposite velocity. You might actually reach the conclusion that they were not simultaneous, and all that's perfectly normal. So that's some of the ramifications. I also gave you the Lorentz transformations, which would allow you to switch from a x prime, t prime, y prime, z prime coordinate system to a x, y, z, t coordinate system. I gave it to you in terms of Galilean relativity, which was just x prime is equal to x minus vt. And there really no prime or unprime on the time. And then, of course, that's assuming that they're moving along the x-axis. And then I gave you the equivalent one, which is called the Lorentz transformations, and that's from special relativity. And that became gamma times parentheses x minus vt is what x is equal to, or excuse me, is what x prime is equal to. Y prime, since that's perpendicular to the motion, turns out to be the same thing as y. Z prime, since that's perpendicular to the motion, turns out to be the same thing as z. And then t prime actually is equal to, again, gamma parentheses t minus vx over c squared, close parentheses. If you need to switch from the prime system to the regular system, what I just gave you was the equations for x prime, y prime, z prime, and t prime. All you have to do is replace the symbols that have primes on them with ones that don't have primes, and vice versa, and then replace v with negative v, and all the equations come out exactly perfect. Okay, so that's a recap of what we found from relativity. There's actually a couple other things that come from it. One thing that's kind of neat, let me show you here. I'm going to start off by writing again the Lorentz transformation. So let me share my screen. I've seen several students log in since I started talking. So before I move on, does anyone have any questions to answer, to ask me before we get started? Yeah, I already asked that before, but I just want to make sure some of the new people had a chance. All right, so this is what we're looking at. And what I told you was we can take a coordinate system, let's say this one right here. And what I'm going to do is I'm going to say, this is my x-axis, this is my s coordinate system, and this is my t-axis. Again, as I told you, it's not uncommon to put t on the vertical axis and x on the horizontal axis in relativity. Okay, there's still, like, you could say a y-axis might be going into the page. Of course, you couldn't fit a z-axis in now because you're talking 4 dimensions, so that doesn't work out so well. But now let me go ahead and draw the other coordinate system. And this one is x prime, t prime, and that's called the s prime coordinate system. The way it's set up is that the actual origins were at the same location and the x-axis were parallel at t equals 0. Of course, they're still parallel, so that's okay too. But the main thing is at t equals 0, these coordinate axes lay right on top of each other. So if you wait for some time t later, then what you're going to discover is that from here to here, this distance is actually equal to v times t. In other words, whatever velocity you see s prime moving with, you multiply that by your time, and that's how far it's moved. If I wish to talk about, let's say, a point in space that's right here, then that point in space in the s prime coordinate system is in fact just plain x prime, and its time, of course, would be whatever that time is there on the on the t axis. Now, for the black coordinate system, the s coordinate system, that distance is in fact that. So we can see that, at least for Galilean relativity, x prime is actually equal to, since this quantity right here is x, it's actually equal to x minus vt. Okay, that's the Galilean relativity, and that's fine. Okay, but the main thing is now I got to put that around in parentheses, and to make the actual Lorentz transformation, I'm also going to put a gamma in front of it. Okay, so this gamma made Galilean go to Lorentz. Okay, now the y-axis and the z-axis are both perpendicular to the motion, so they're essentially unaffected. So that means y prime is going to be equal to y, and that means z prime is going to be equal to z. T prime, at least in Galilean relativity, is actually equal to t, but in Lorentz, that's not the case. So in fact, what you get is parentheses t minus vx over c squared, and then you got to multiply a gamma there. So in this case, you had to add this and this to go from Galilean relativity to Lorentz. Now, again, Lorentz made up these equations to try to save the ether, and it turned out to be the equations were exactly right. But when Einstein comes along and makes his two postulates, you can see not only that Einstein's right, but now you've got a good physical reason for it, other than to say, oh, ether doesn't exist. Okay. So that's the transformations, Lorentz transformations, and you just got to be careful. You'll notice when you start doing chapter 36, there's one problem where it sort of is giving you, well, you might think you're being given x and t, or x prime and t prime, but in fact, you're being given like x and t prime, or you're being given t and x prime. So be careful in noticing exactly what you're being given. Now, if you want to switch to the other system, in other words, if you want to convert from the prime system to the unprimed system, then this is how that works. And this is what I was hinting to a second ago. This means that x, y, z, and t are going to be given by, now all I'm going to do is replace the primes with unprimes and the v with negative v. So I'm going to put a gamma here. I'm going to put a x prime here, a plus here, and a v t prime there. This is going to be y prime. This is going to be z prime. And this one is going to be gamma t prime plus vx prime over c squared. And that's the transformations back to the non-prime coordinate system. In other words, to S. Okay. Now, this is the reason I wrote this. I wanted to show you one more ramification, and it's called the invariant interval. So here is the invariant interval. And you can prove this for extra credit if you so desire. Actually, let me not call it proof. Let me call it prove for extra credit. Okay. What the invariant interval is if you multiply c squared t squared and then subtract from that x squared, y squared, and z squared, then that will actually be equal to c squared t prime squared minus x prime squared minus y prime squared minus z prime squared. Of course, the y prime and the z prime are just trivial. They're identical, so you can cancel that out from the beginning. But the main thing is this interval happens to be invariant, meaning if you take the left-hand side and plug in those equations on the right-hand side above it, the x, y, z, and t, if you plug those in there, work out the algebra, you'll actually turn out to get this right-hand side. Now, it's also called, because proper time is defined to be the time interval between two events that happen to happen in the same place in a coordinate system, you can also say c squared delta t squared minus delta x squared minus delta y squared minus delta z squared is equal to c squared delta t prime squared minus delta x prime squared minus delta y prime squared minus delta z prime squared. And actually this delta y was really ugly, so I'm going to fix that. Okay, so that is another version of it. In other words, instead of now having just x, y, z, and t, you could have x2 minus x1 would be delta x, y2 minus y1 would be delta y, z2 minus z1 would be delta z, and t2 minus t1 would be delta t. Okay, you can do that. And if you realize what the proper time is, tau is equal to proper time. Actually, I should have put those further apart. Let me kill that. Which you could also say delta t0, because that's what we actually called it last time. That's a proper time interval. That occurs specifically when the two events, x2 minus x1, y2 minus y1, z2 minus z1, t2 minus t1, when they all happen in delta x equals delta y equals delta z equals 0. So this is also c squared delta t 0 squared. So that's another part that comes in handy, is the invariant interval is technically just c squared times delta t squared. Let me write that a little clearer. I'll do this. I'm going to put the exponent of 2 right here. I'm going to say c squared delta t 0 squared. Okay. So that's something you can prove. I will put a assignment on the this week's module in Canvas, and you can turn in that work there. Again, what you're going to do is work it out by hand. You could type it up if you wanted to. I do not want you necessarily wasting your time doing that unless you're just wanting to play with the equation editor in Word. But ultimately, you're going to have to save it as a PDF and upload it there. And I will give you, obviously, I will replace your lowest grade with 100 for doing that. So it's not as hard as you think. It's just some algebra. You just got to put, and I advise you just have to put these equations into it. But I advise using this version, not the other version, because it's a little more complicated doing the other version. But whichever one you find useful, go ahead and do it. Any questions on that? Okay, so that's another ramification of special relativity. Now that I've discussed that, I will tell you some neat stuff about it. That invariant interval, for instance, you can use that to actually derive length contraction, which I gave you the formula for. You can use it to derive time dilation, which I gave you the formula for. You can even use it to help you come up with those energies and how they're actually defined. So that's kind of interesting. What I thought I'd do now is I want to show you a specific example of using relativity. And to do that, what I want to do is show you something neat that I pulled up. So let's stop sharing this screen. And now I'm going to share screen. But this time I'm going to share this one. Okay, so this is actually a link from a Wikipedia page. So I did a Google search for GPS satellites and pulled up the Wikipedia page, because it turns out that just about every time I open up a Wikipedia page about science or math, it's really good, and it has a lot of good resources, and I never find any BS on it. The only thing I occasionally find is a typo or something like that. So I do recommend you using that. But what this is basically a picture of the Earth orbiting or rotating, and then we're not paying attention to its revolution. We're just paying attention to its rotation. And it has various satellites that are used for GPS, specifically that blue one right there, GPS. It shows you roughly how far above sea level it is. It shows you roughly what its velocity is. I'm going to take that velocity to be, notice down at the bottom, that hash mark on the left-hand side of the vertical line says 7,000 miles per hour. And then I go up one, let's pretend for a second just to see if it's true. I go up one right over the word orbital speed, and that one sticking out to the left, I think might be 8,000. And then the next one would be 9,000. And then all of a sudden I realized, oh yeah, that's right, because the next one's 10,000. So I would argue that probably that blue satellite has a velocity of, let's say, 8,700 miles per hour. Okay. So I'm going to use that velocity to convince you that we actually have to use relativity when dealing with the GPS satellite. Okay. So this is sort of like the problem we're working, a relativistic correction, but I just pulled up my own data with regards to the velocity. What I want to do is now make use of this specific satellite, the blue one that says GPS, and I'm going to say that that velocity, which is right here, is roughly 8,700 miles per hour. Okay. Now I'm going to stop share with that one. And I'm going to go back and share my iPad screen. So what I want to solve here is the following. Whoa, I just put a big eraser in there by accident. A GPS satellite. And I really feel like I need 2 T's in there, but it never is. Actually 3 T's total. But a GPS satellite has a speed of 8,700 period miles per hour. So I'm going on the assumption that's 4 sig figs. It's just a rough estimate, so I don't care too much. What I want to do is show that the satellite must use relativity to give accurate positions. Does anybody not know what GPS is? Nobody spoke up, so I'm assuming that means y'all do know what it is. So it positions us on Earth, and in fact, you can get within a few centimeters of where you are, unless you've got a lot of like if you're in the middle of downtown New York or Salt Lake City, Utah. Sometimes those buildings can mess it up a little bit where you can't figure out where you are to within maybe a meter or so. But if you're away from huge mountains and you've got a clear view of multiple satellites, your GPS can place you within centimeters of where you really are, both in longitude and latitude, as well as in altitude. So I'm going to say it's positions. So in order to do that, it has to know precisely what the time is and stuff like that. So that's the kind of corrections that we're going to make, because ideally you need to know exactly how long it takes a signal to come from the satellite to a person on Earth and to come from a person on Earth to a satellite. So let's calculate the actual time dilation that results from that. So here I go. Solution. Delta t is equal to delta t 0 over the square root of 1 minus v over c quantity squared, which is also equal to gamma delta t 0. And delta t 0 is really going to be our satellite time, and delta t is going to be the time that we measure. So that's the satellite time, and this is us. Okay. Now v is equal to 8.7, and this is really the way I should write it. If I want to call it 8,700, I should write 8.700 times 10 to the third miles per hour. Now, what I'm going to do is I am going to make use of the fact that 1 mile is 5,280 feet, and that 1 foot is equal to 12 inches, and that 1 inch is exactly equal to 2.54 centimeters, and then that 100 centimeters is equal to 1 meter, and then that 1 hour is equal to 3,600 seconds, and that's going to give me exactly my velocity. So if I put in 12 sig figs, out would pop out 12 sig figs accurately. So I'm going to do 8.7 times e to the third times 5280 times 12 times 2.54. And now I'm going to divide that by 100 and hit equals. And then I'm going to divide that by 3,600. And that gives me about 3,000. Whoa, Nelly. That gives me about 3,889 meters per second. Okay. Now, I need V over C. And of course, beta is what I told you the symbol for V over C is. So that's V over C, which I can say is 299,792,458. Oops, I put that in the wrong space. Stupid me. I started writing it and forgot I put it on the top instead of the bottom. Okay, so that's going to be 3,889 meters per second over 299,792,458 meters per second, which should give me, let's divide this by 299,792,458, 299,792. Yep. That gives me 1.297, that's 4 sig figs, times 10 to the negative fifth. Okay, so that's what beta is. Now, this is going to be a little bit difficult, but what we have is 1 minus beta squared to the negative 1/2 power. And if you actually look in the front cover of your book, you'll find that binomial thing again. And this is approximately equal to 1. Now, since it's a minus here, that's going to become a minus here. And then it's going to be negative 1/2. That's the actual exponent, is negative 1/2. And then times the x, which is beta squared. So I'm now going to take that and multiply it by 1.297 times 10 to the negative fifth squared, because what we're saying is 1 plus or minus x raised to the n power is approximately equal to 1 plus or minus n times x. Now, there's other terms too, but this is for x being much, much less than 1, which clearly x is way less than 1, because beta, which isn't even squared yet, is 10 to the negative fifth. Once I square that, I get 10 to the negative 10th. So it's really a big deal. So this is going to be, I squared it and got 1.68 times 10 to the negative 10th. So let me write that down. 1.683 times 10 to the negative 10. Now I'm going to multiply that times 0.5. And then I'm going to add that to 1. And this is where stuff gets crazy. But it's basically 1 plus 8. Whoa. 1 plus 8.415 times 10 to the negative 11. That's what basically the gamma is. Okay. So what that means is delta T is equal to gamma times delta T 0, means that this is approximately equal to 1 plus 8.415 times 10 to the negative 11th times delta T 0. Okay. So the atomic clocks that are used for GPS actually, let me just, I'll write that differently. For GPS are good, are precise, I should say, are accurate to 1 part in 10 to the 13th. So that means basically you can pick up a problem at the 13th decimal place, essentially. So what we see here is delta t is equal to 1 plus 0.123456789 10 and then 8415 times delta t 0. So clearly this is fewer decimal places than 13. This is in fact only 9 zeros, implies we need relativity. Okay. So that's it. Anybody have a question on that? Now you could actually calculate, for instance, the percent difference. Let me show you quickly how that would be. So if I wanted to calculate percent difference, I could say percent difference is equal to delta t minus delta t 0. Actually, delta t should be, t0 should be longer. So I don't really want this to be negative. So I'm going to say delta t0 minus delta t over delta t, like that. Delta t0, sorry about that. And then basically times 100 to make it into a percent. So if I do this, then what I see is delta t minus delta t0 I got was 8.415 times 10 to the negative 11th. So delta t was equal to 1 plus 8.415 times 10 to the negative 11th times delta t 0. So I can say percent difference is approximately equal to, I'm going to write delta t 0 times 1 minus, now this part was 1 plus 8.415 times 10 to the negative 11th times delta t 0. So that's why I can just pull that delta t 0 out in front, and then all this will be divided by delta t 0 and then times 100%. So we get, in this case, you can see the delta t's cancel out, and basically 1 minus 1 gives me 0. And lo and behold, of course, I clearly made it negative, even though I tried not to. But that came out to be 8.415 times 10 to the negative 9%. Okay, again, that's way less than 1 part in 10 to the 13, which 1 part in 10 to the 13, I think y'all can tell automatically, is 1 times 10 to the negative 13. So clearly, even if we didn't express it as a percent, we could also have said negative 8.415 times 10 to the negative 11. You still see that clearly that's a bigger chunk than 1 in 10 to the 13. So any questions on that? Nothing? Okay, well that's good news. I assume that means y'all are getting it. Let's work a couple other problems just to see uh, some of the stuff that we're dealing with. For instance, length contraction. Uh, I can already, for one thing, think about trying to make something a very specific size difference. So, for instance, we know that gamma is defined to be 1 over the square root of 1 minus v over c squared. And we know that's the same thing as 1 over the square root of 1 minus beta squared, right? But what if we want to know what beta gives us specific gamma? So if I take this and square both sides, I get gamma squared is equal to 1 over 1 minus beta squared. That gives me, in fact, 1 minus beta squared is equal to 1 over gamma squared. Well, that also gives me 1 minus 1 over gamma squared is equal to beta squared. So ultimately, I can say that beta is equal to, I'm going to make this 1 here. I'm going to make that gamma squared over gamma squared. So I then get the square root of, oops, let's not change that color to red. I then get the square root of gamma squared minus 1 over, of course, this would have been the square root of gamma squared, but I went ahead and reduced it. So, and I think I might have did this calculation the other day, but I left off this exponent of 2 under the radical. So check your work to make sure I didn't make that. I just remembered it today when I was working in class. So there might have been a mistake. There might not have been. I might just be misremembering. But here's the deal. If I want gamma to make something a time interval twice as long or a length half the length, then I want gamma equals 2. That clearly implies that beta is going to be equal to the square root of 3 divided by 2, which is 0.866 roughly. Okay, so if I go at 86.6% of the speed of light, then my gamma factor becomes 2. Well, that's nice because if I want to make a 10-foot barn look like, or a 10-foot board, make it look like it's a 5-foot board, then all I have to do is travel at 86.6% of the speed of light. So that's length contraction. Let's look at an example now. Show that at 86.6% of C, a 10-foot board is about 5 feet long. Okay, so here's our solution. We know the Lorentz contraction or length contraction formula says that L is equal to L0 over gamma. So L0 is basically the proper length. Remember, proper length, again, that's a English translation of a German word, and it's not that good of a translation. A better translation might have been relevant length or significant length, meaning it's the one that's significant to the person. So, for instance, if you're talking about proper time, why would a person care what time it is based on someone else's clock? They would want to know what time it is or how much time passed by on the clock sitting right next to them. So that's the appropriate or the preferred time. So that's what a better interpretation of proper time should be. Similarly, for a length, why would someone in a car want to know how long their car is as seen by someone that they're riding by? Wouldn't it be better to know how long your car is to you because you're the one that's going to try to fit it in a parking space or something like that? So in this case, L0 is going to be 10 feet, and I want L to be 5 feet. So gamma has to be, in fact, solving for gamma, gamma has to be L0 over L, which equals 10 feet over 5 feet, which equals 2, which is equal to 1 over the square root of 1 minus beta squared. And if I put in beta equals 0.86, I'll have 1 over the square root of 1 minus 0.866 squared. And I put a question mark equal to there because when I actually do this, I'm going to do 1 minus parentheses 0.866. And now I'm going to square that quantity, close parenthesis. I get 1 minus, or excuse me, I get the square root of 0.2500. So this side equals 1 over the square root of 0.2500. And I think you can see that that is clearly true. Because notice, anybody know what the square root of 1/4 is? What's the square root of 1/4? Anybody?
1/2.
1/2. And 1/2 in the bottom is the same thing as 2 in the top. That's why I said it's true. Did everybody get that? All right. So that's one particular problem. That's a length contraction problem. Let's work on a relative velocity problem. So it turns out, and I gave you this before, but it turns out that the velocity of A as seen by C. Now, in this case, I'm just talking about the S coordinate system and the S prime coordinate system as I drew them before. So everybody has to agree which direction is the positive X direction. And the X prime and the X direction are both the same direction. And in fact, at T equals 0, the origins are even at the same spot. Okay. Now what I'm going to say is I'm only dealing with velocities that are parallel to the x-axis. So I'm not going to write a vector symbol on it. I'm just going to write it as magnitudes because I'm only dealing with that. So this turns out to be just like the Galilean formula, which is the velocity of A as seen by B plus the velocity of B as seen by C. That's the Galilean formula. Notice the middle two subscripts are the same. That's one key part. And the outer two have to match the two subscripts on the left-hand side. So all of this matches what we learned from Galilean relativity. But here's the relativistic correction. It's 1 plus VAB VBC over C squared. So that's the actual relativistic formula. So let's imagine down here, I have a planet Earth. So here's an example. I want to know what is the velocity of B as seen by A. And I want to know what is the velocity of the photon. So I put a P there because that's what photons starts with respect to A. Okay. Now, what do I mean by that? Well, what I have here is the Earth, say. Okay, that was not helpful at all. And I have ship A traveling with VAE equal to 3/4 the speed of light. I have over here ship B traveling with a velocity of V BE equals negative 7/8 C. And then I also have a little photon torpedo that shoots out a little photon. And the velocity of the photon, oops, I should put that back in red and blue. The velocity of the photon as seen by ship B is negative C. Okay. Now, the other rule that has to go along with this is this. The velocity of I relative to J is equal to the negative of the velocity of J relative to I. Okay. That just means, hey, we all got to agree which way is the positive direction and which way is the negative direction. So if we say north is positive, if I'm going 60 miles per hour north, then I look at you, and to me, it looks like you are going 60 miles per hour south. And that's all that says is the velocity of you with respect to me is negative 60 miles per hour, whereas the velocity of me with respect to you is positive 60 miles per hour. So that's why that Vij equals negative Vji. So let's use this. First off, I'm going to say solution. The velocity of A as C, or excuse me, I want the velocity of B. Go back. Okay. I want the velocity of B as seen by A. According to our normal formula, that should be VBA plus VA, oopie doopie, VBE, excuse me. VBE plus VEA over 1 plus VBE VEA over C squared. Now, I don't have VEA, but VAE is actually the velocity of A as seen by Earth is actually 3/4 C. So the velocity of E as seen by A is negative 3/4 C. So I can actually do this. I can say VBA is equal to VBE, which is negative 7/8 C, plus now I've got to put in VAE, which is the negative of this. So I'll say plus negative 3/4 C. All that's going to be divided by 1 plus. Now I'm going to have negative 7/8 C, negative 3/4 C, all that over C squared. So you can see these C squareds cancel out with these two C's. We can also see that that numerator is going to become 7/8 or negative 7/8 plus negative 6/8, which would be negative 13/8 C. And then the bottom, notice that's going to become 1 plus, because negative and a negative is a positive. If I multiply those two, I get 7 times 3 is 21, and 8 times 4 is 32. So I'm going to make the 1 32 over 32. Okay. So now I get negative 13/8 C divided by, check this out, I add 32 to 21, I get 53. And then I have that divided by 32. So this becomes negative 13/8. Ooh. Negative 13/8 times C. Now I've got to flip that 53 over 32 over to multiply it by the top. So the 32, which is also 8 times 4, is going to cancel out with the 8, which is also 8 times 1. And down here, the 32 is going to become 53. And you can see that this 8 cancels out with that 8. And I am left with 4 times 13, which is 52. Negative is still there, of course. So negative 52. Actually, let me write that a little. Well, hey, the one time I try to get a eraser, it won't give it to me. Okay. So this would be negative 52 over, now you see what's left is 53C. So that's how fast the ship is approaching the other ship. That's sort of like you and I riding towards each other on the interstate. If I'm driving 60 north and you're driving 60 south, relative to me, you're coming at me at 120 miles per hour. That's part of the problem with head-on collisions. There's very little reaction time with a head-on collision because you're not going 60 miles per hour relative to me. You're actually going 120. In this case, notice Galilean-wise, we should have gotten 13/8, which would be basically 1 5/8 or 1.625 times the speed of light. But the actual formula that I did derive in my YouTube channel, which I showed you right here, that formula actually gives us the correct formula, which is that the velocity of B relative to A is negative 52/53, just a shade under 1C. So that's part A. Now we can do part B, and part B is where I want to know the velocity of the photon relative to A. In other words, so this ship is coming at me at a relative speed of 52/53 the speed of light. That's pretty darn close to the speed of light, right? What's 52 over 53, in fact? Well, 52 divided by 53 is 98.11% of the speed of light. Now it's 98.11% of the speed of light, and then it shoots a photon at the speed of light relative to it. So you can imagine, wow, this thing's going to be going really way over the speed of light. So let's see what it actually is. So for part B, I'm going to say the velocity of the photon relative to A is the velocity of the photon relative to B. Notice I chose B because I happen to have VPB. So that's plus the velocity of B as seen by A. Now that matches our criteria. The middle subscripts match each other and the outer ones match the left one. So I've got it all correct. That's going to be 1 plus VPB VBA over C squared. So in this case, I'm going to get the velocity of the photon as seen by B. That's going to be negative C plus the velocity of B as seen by A. That's negative 52/53 C, as we just calculated. And then all this is going to be divided by 1 plus negative 1C times negative 52 over 53C over C squared. Again, you can see the C squared cancels out with the C, but you might also see that I get 53 over 53 is what negative 1C becomes. It becomes negative 52, or excuse me, negative 53 over 53. So I get negative 105 over 53C. And then down here, I'm going to get 53 over 53 plus 52 over 53, which I think y'all can tell that's clearly 105 over 53. So I get, in fact, negative C, which is exactly what Einstein told us it would be. He said the speed of light is a constant independent of the motion of the source and independent of the motion of the observer. So since a photon is the particle of light, the velocity of the photon as seen by ship A is in fact negative c, and it's negative again because everybody has to agree which direction is the positive direction and which direction is the negative direction. All right, any questions on that? None deal. Okay, well, we technically only have like 2 minutes left of class. I would have chosen to for instance, calculate some of the energy problems or something like that. So for instance, in section 3611, there's some examples that I would have done for you or something like them. So it says, for instance, example 3610. Let me just share that screen with you and show it to you real quick. So I'm going to share a screen now, and I'm going to share this one. Okay, so this is example 3610. It says a pion's kinetic energy. So a pi zero meson, which has a mass of 2.4 times 10 to the negative 28 kilograms, travels at a speed of beta equals 0.84, or you could say V equals 0.84 c. That's what this velocity is. Now, with that, it says, what is the kinetic energy? And then compare that to the classical equation. Well, remember the kinetic energy that we found for relativity was gamma minus 1 in parentheses times mc squared. So what they do is immediately go to calculating gamma. That's 1 over the square root of 1 minus 0.84 with the 0.84 in parentheses squared. That gives me a gamma factor of 1.84. I subtract 1 from that because that's the way you get gamma minus 1. And therefore, it becomes 0.84 times the mass of the pion, 2.4 times 10 to the negative 28 kilograms, times the square of the speed of light. They only gave us 2 sig figs, so you really only need 2 sig figs for the speed of light. And that's 3.0 times 10 to the 8. So you ultimately get 1.8 times 10 to the negative 11th joules. Classically, you do 1/2 mv squared, and your book takes the time to calculate that. You see that 7.5 times 10 to the negative 12. So the kinetic energy is way less from the classical formula than the relativistic formula gives you. So that's a very typical problem, straightforward. Here's another one. In this case, they're asking you for calculate the energy released in the decay. So in this case, you're really calculating the change in masses. You went from an initial mass of 232.0716, which is the mass of uranium, to the mass of thorium, which uranium decays into. That's 228.02874. And what they want you to do is calculate that change in mass. Well, you actually can subtract those two masses and get the new mass, multiply that by c squared, and that's the actual energy given off. Now, in principle, there's a lot of different ways for things to nuclear decay. Normally, one of the ways that it does it is a bigger molecule, or in this case, a bigger nucleus, I should say. A bigger nucleus decays into 2 smaller nuclei, one of which being an alpha particle and the other one being, in this case, thorium. Well, that alpha particle has an mc squared, so I've got to take that into account too. That's some new created mass. But once you take that plus the mass of the new thorium, that's the total mass that came out of the uranium. But lo and behold, that mass, if you add the 228.02874, the mass of the thorium, to the mass of the alpha particle, which is 4.00260, that's the total mass after the nuclear reaction. And then you subtract that total mass from the 232.03716. That's the difference in mass. That multiplied by c squared is how much energy the photon, or excuse me, the alpha particle and the nucleus or the thorium, in other words, have to be used as, say, kinetic energy. There also can decay spitting out a positron, which is basically an electron with a positive charge, or it can decay spitting out a neutron, all sorts of weird stuff. Your book talks about that in the chapter on nuclear physics, but that's basically it. So you guys, of course, free to go. I'll wait for the last person to leave. And next time we'll jump into chapter 14, and then the time after that we'll jump into chapter 15. So we're literally spending about a day on each of those. Any questions?
Hey, Mr. Younger,
Yes, sir.
When's the final exam planned to be?
On my calendar, I'm looking at that right now. The final exam for your class, which meets on Mondays and Wednesdays, will be on the 26th.
Okay.
And I should have the practice final up by next week, if not even earlier. I suspect I'll have it up tonight or tomorrow. But the practice final and some practice tests, or tests plural, will be posted as well.
Okay, and I'm assuming the best way to study and prepare for the final will be doing those tests.
Yes, you should probably get the homeworks done so you can understand them enough to not just look up answers on the practice test and then just do the practice test a bunch of times. That's the best way you can prepare for any test or any final exam or any midterm exam in my classes.
Okay. Thank you.
No problem. So 2 weeks from tonight is the final. Woohoo!
What chapters will they be at?
So the final will be chapters 1 through 11, plus 36, plus 14, and plus 15.
All right.
I'll put that in the notes too, so when I post them on Google Docs, you'll see it. Anybody else have any questions?
I had a quick question.
Go ahead.
Let's see. Do we have any more of those online tests due?
Yeah,
Coming up?
I'm going to put up some tonight or tomorrow. So yeah, there absolutely is going to be at least one more. What I probably will do is I'll probably make 2 more, and I'll drop your 2 lowest instead of your 1 lowest. But I
Okay.
definitely recommend taking it.
Okay. So
Okay.
none due this Sunday or anything like that,
No,
probably
no,
next
I'll
week.
give you plenty of time. I'm not going to stiff you like that.
Thank you.
No problem. Anybody else?
Yeah, so then all of the rest of our homework will be due on the 30th.
Yeah, I've changed it. You can see I did a little bit different dates for the relativity in chapter 11, but everything else is just going to be due on the 30th. So check whatever it says in my lab and mastering. That's what I decided on.
And then there will be no more class on the 1st.
That's correct. You don't have to show up for anything there. And in fact, talk to your lab instructor. I don't know which lab she's planning on covering, but she might not even have lab next week. It all depends. She has a way where she can, do a lab final if she wants on one day, or she might give you some extra office hours to make up for one of the days. But usually that last week you don't have a lab.
Perfect. Thank you.
No problem.
Professor, you may have mentioned this before, and I may have just missed it, but is there any like estimated time on when the midterm redo will be?
Yeah, I'm having some difficulty. It turns out that that's really not fun to grade. So I apologize, but yes, it's not fun to grade. I will have it ideally finished this weekend, or at least by Monday, just because I have to. So I
Okay.
apologize.
Yeah, I know
for
it's a
that.
lot.
Yeah, it does matter a lot, but I don't mind too bad. keeping y'all scared about your grade, but I really should go ahead and get it done. So I will do that. But basically, it'll be done by Monday.
Okay, great. Thank you.
Okay.
How are they
Sorry,
looking?
everybody. Anybody else? That was Didio, Brianna, Carter, Gavin, Ronnie, Johnny, Mickey, or Mike. Anybody else have any questions? All right, keep an eye on your email when I post stuff like a new test or a new practice test or something like that, or if I change any homework dates or decide not to cover a chapter or something, I will send you emails about that. So just keep an eye on your emails. Have a great weekend. Stay safe. Do physics every day. That's just the better people really do that. That's what makes the difference between really good people versus really bad people. Okay, I'm lying a little bit on that, but definitely, it definitely helps you. The more days you do them in a row, the better off you'll be at your physics. So hopefully I have you guys this summer or in the fall for 242. Carter or Gavin, do y'all have any questions? I'm going to log out otherwise. It appears.
Thank you.
No problem. Have a good one, Gavin. Bye-bye. Bye-bye. See ya.